A restless volcanic landscape has delivered its most powerful warning in 4 decades, forcing scientists to confront a question that extends far beyond a single earthquake. When the strongest tremor to strike Campi Flegrei in approximately 40 years shook one of Europe's most densely populated volcanic regions, was it simply another release of long building pressure, or did it reveal that the forces reshaping the caldera remain far from equilibrium? Why has the earthquake that alarmed residents become only one part of the scientific investigation, while the hundreds of smaller tremors that followed are now attracting equal attention from volcanologists across Italy? Those questions intensified on Friday evening as Campi Flegrei, the vast volcanic caldera immediately west of Naples, experienced its strongest earthquake since the major bradyseismic crisis of the early 1980s. The magnitude 4.7 event rattled homes, damaged buildings, disrupted transportation, and sent thousands of residents rushing into streets and open spaces. Even as emergency crews assessed the immediate impacts, scientists began examining a much broader sequence unfolding beneath the surface. The main shock was not an isolated event, but part of an evolving pattern that continues to provide valuable clues about the behavior of one of the world's most closely monitored volcanic systems. At precisely 7:46 in the evening local time on Friday, July 31st, 2026, the earthquake struck with its epicenter near the Solfatara crater in Pozzuoli. According to Italy's National Institute of Geophysics and Volcanology, or INGV, the earthquake originated at a depth of approximately 3 kilometers, or about 1.9 miles. Such a shallow focus allowed very little seismic energy to dissipate before reaching the surface, producing intense shaking across communities built directly above the volcanic system. Residents described a sudden, violent jolt that sent furniture sliding across floors, cracked walls inside homes and businesses, and prompted families to evacuate within seconds. Portions of the electrical network experienced temporary outages, while railway services and local transportation were suspended until engineers completed safety inspections. Emergency responders quickly assessed older masonry buildings, many of which are especially vulnerable to repeated shallow earthquakes. Although the event was modest compared with the destructive tectonic earthquakes that have struck other parts of Italy, its location beneath an active caldera made it especially significant from both a scientific and civil protection perspective. For the people of Pozzuoli, the earthquake was another reminder that the ground beneath their community has remained in motion for years. Campi Flegrei has been undergoing a prolonged episode of bradyseism, a process in which the land slowly rises or falls as underground pressure changes within the volcanic system. During the current phase of unrest, thousands of earthquakes have accompanied steady ground uplift of approximately 6 feet or nearly 2 meters. While most of these tremors have been too small to cause widespread damage, they collectively demonstrate that the caldera remains an active and evolving geological system despite the absence of an eruption. Friday's earthquake nevertheless marked an important milestone. It was the largest seismic event recorded within Campi Flegrei since the unrest that forced large-scale evacuations during the early 1980s, making it one of the most significant earthquakes observed during the current period of volcanic activity. That distinction immediately raised an important scientific question. Had the earthquake released a substantial portion of the accumulated stress beneath the caldera, or was it the beginning of a more complex sequence? Monitoring stations soon provided the first indication that the story was far from over. As the hours passed, instruments continued detecting earthquake after earthquake beneath Pozzuoli and the surrounding volcanic field. What initially appeared to be a single damaging event rapidly evolved into another extensive earthquake swarm. According to INGV, approximately 191 earthquakes have now been recorded since the magnitude 4.7 main shock, with the vast majority remaining significantly smaller. For residents trying to rest after the strongest shaking had passed, every new tremor revived concerns that another powerful earthquake might follow. For volcanologists, however, the sequence revealed something equally important. Despite the growing number of earthquakes, none has exceeded the magnitude of the initial event. That pattern is being examined closely because it provides valuable insight into how stress is being redistributed within the fractured volcanic crust. While it remains impossible to predict future earthquakes, the absence of a larger event so far suggests that the caldera may be accommodating part of the accumulated strain through numerous smaller ruptures rather than a single progressively expanding fault break. Understanding why this earthquake occurred requires looking beyond conventional tectonic processes. Unlike earthquakes generated along major plate boundaries, the seismic activity at Campi Flegrei is closely tied to changes occurring within the volcanic system itself. Beneath the caldera, a complex network of fractured rocks is continually subjected to shifting pressures as volcanic gases, heated groundwater, and deeper magmatic processes interact. Those forces gradually weaken sections of the crust until individual fractures suddenly slip, releasing energy as shallow earthquakes. Rather than representing a single fault capable of producing one enormous rupture, the caldera behaves as an interconnected system of countless fractures responding to changing underground conditions. That distinction helps explain why Campi Flegrei often produces earthquake swarms instead of isolated events. As pressure redistributes beneath the caldera, one fracture can alter the stresses acting on nearby rocks, encouraging additional fractures to fail over hours or even days. The resulting sequence resembles a chain reaction in which numerous small adjustments occur throughout the volcanic crust. Each earthquake slightly changes the stress field, sometimes relieving pressure locally while transferring additional stress elsewhere. This continual redistribution is one reason why scientists closely monitor not only the largest earthquake, but also the location, depth, and timing of every smaller tremor that follows. The latest sequence has therefore become an important source of scientific data. By mapping where each earthquake occurs, researchers can determine whether seismic activity remains concentrated around existing hydrothermal zones or begins migrating toward other parts of the caldera. Migration patterns are especially valuable because they may reveal how underground fluids are moving through newly opened fractures. A stationary swarm often reflects localized stress adjustments, whereas a migrating sequence can indicate that pressure changes are propagating through different sections of the volcanic system. Although no single pattern can reliably forecast future activity, these observations help scientists distinguish between routine unrest and more significant changes occurring beneath the surface. Particular attention has focused on the area surrounding Solfatara, where the magnitude 4.7 earthquake originated. Solfatara is one of the most active hydrothermal regions within Campi Flegrei, characterized by fumaroles that continuously release steam, carbon dioxide, and sulfur-rich volcanic gases. Beneath the crater lies an extensive circulation system in which groundwater descends through fractured rocks, becomes heated by the underlying volcanic heat source, and rises back toward the surface, carrying dissolved gases and minerals. This constant movement of hot fluids gradually alters the mechanical strength of the surrounding rocks, while also influencing underground pressure. Over time, these processes create conditions in which even modest pressure increases can trigger repeated seismic activity. Hydrothermal systems are inherently dynamic because they respond to changes in temperature, fluid pressure, and permeability. When new fractures develop, they may temporarily allow gases and steam to escape more efficiently, reducing pressure in one location while redirecting fluids into another. Conversely, if mineral deposits seal existing fractures, gases may become trapped until pressure builds high enough to reopen pathways through the surrounding rock. Scientists therefore view every earthquake as one component of a much larger system in which rock deformation, fluid circulation, and gas migration constantly influence one another. One reason Campi Flegrei commands such extraordinary scientific attention is that these processes unfold beneath a densely populated urban region rather than an isolated volcanic landscape. Residential neighborhoods, transportation corridors, industrial facilities, and centuries-old historical structures occupy ground that is slowly deforming in response to volcanic activity below. Even relatively modest earthquakes can therefore have consequences far beyond their measured magnitude because they repeatedly stress buildings already affected by years of gradual uplift. Engineers evaluating structures after Friday's earthquake are considering not only the effects of the latest shaking, but also the cumulative impact of thousands of previous earthquakes experienced during the current period of unrest. Historical records demonstrate that this pattern of uplift and seismicity is not unprecedented. During the major bradyseismic crisis of the early 1980s, the ground beneath Pozzuoli rose dramatically, while earthquake activity intensified over several years. Tens of thousands of residents were eventually relocated because repeated shaking had weakened buildings and raised concerns about public safety. Although the present unrest shares several characteristics with that earlier episode, scientists caution against assuming the two periods will follow identical paths. Every phase of volcanic unrest develops under its own unique combination of underground pressure, fluid movement, and crustal conditions, making direct comparisons useful but not definitive. For that reason, researchers are relying on continuous observations rather than historical analogies alone. Every new earthquake is analyzed alongside measurements of ground deformation, volcanic gas emissions, and changes within the hydrothermal system. The objective is not simply to determine where earthquakes are occurring, but to understand whether multiple monitoring techniques are pointing toward the same underlying process. A temporary increase in seismicity, without corresponding changes in other observations, may indicate one type of underground adjustment, while simultaneous changes across several independent monitoring systems could suggest a more significant evolution within the caldera. This comprehensive approach reflects decades of scientific progress in volcanic monitoring. Modern instruments can detect minute ground movements, precisely locate tiny earthquakes, and continuously measure changes in volcanic gas composition with a level of accuracy unimaginable during earlier periods of unrest. Instead of relying on any single measurement, volcanologists integrate thousands of observations into computer models that help explain how pressure is changing beneath the caldera. Although these tools cannot predict exactly when earthquakes will occur or whether volcanic activity will escalate, they greatly improve scientists' ability to recognize subtle trends that might otherwise go unnoticed. As scientists continue analyzing the growing volume of data collected since Friday's earthquake, one conclusion has become increasingly clear. The significance of this event lies not only in its magnitude, but in the detailed snapshot it provides of a volcanic system that has remained persistently restless for years. Every earthquake, every millimeter of ground movement, and every change in volcanic gas emissions adds another piece to an exceptionally complex geological puzzle. Rather than viewing the magnitude 4.7 earthquake as an isolated incident, researchers are treating it as one stage within an ongoing sequence that may reveal how Campi Flegrei is responding to years of continuous uplift and underground pressure changes. One of the most important questions now facing volcanologists is whether the recent swarm represents a temporary adjustment within the caldera or marks the beginning of a longer period of elevated seismic activity. Earthquake swarms at active volcanoes can persist for days, weeks, or even months before gradually declining, while others evolve through multiple phases separated by periods of relative quiet. The duration of the current sequence will depend on how quickly the underground stress field reaches a new equilibrium and whether additional pressure continues to build within the volcanic system. At present, there is no reliable scientific method capable of predicting exactly when such sequences will end, making continuous monitoring the only dependable means of tracking their evolution. Researchers are paying particularly close attention to the precise distribution of earthquakes beneath the caldera. Modern seismic networks allow scientists to locate individual earthquakes with remarkable accuracy, creating three-dimensional maps of where fractures are occurring beneath the surface. If future earthquakes remain confined to the same general area and depth, the sequence may indicate that stress is being released within an already active portion of the volcanic crust. A significant migration of seismic activity into new areas or toward different depths, however, could point to changing underground conditions that would require even closer evaluation. These subtle shifts often provide valuable clues about how pressure is moving through the fractured rocks beneath Campi Flegrei. Ground deformation will remain another critical indicator in the weeks ahead. For years, global navigation satellite system stations and satellite radar observations have documented the gradual uplift affecting much of the caldera. Scientists will now compare those measurements collected before and after the earthquake sequence to determine whether the recent seismic activity has altered the rate or pattern of deformation. In some cases, earthquake swarms can temporarily relieve localized stress without significantly affecting the broader uplift trend. In others, changes in deformation may reveal that underground pressures are continuing to evolve. Interpreting those measurements requires careful analysis over time, rather than relying on any single observation. Volcanic gases will also continue receiving close scrutiny. Carbon dioxide, sulfur dioxide, and other gases escaping through fumaroles provide direct evidence of processes occurring beneath the surface. Scientists routinely analyze both the quantity and chemical composition of these emissions, because changes can reflect evolving conditions within the hydrothermal system or deeper volcanic source regions. Gas data alone cannot determine whether volcanic activity is increasing, but when evaluated alongside seismicity, deformation, and temperature measurements, they help build a far more complete understanding of the caldera's behavior. Equally important is recognizing what the current observations do not indicate. Although the earthquake has understandably heightened public concern, earthquake activity by itself does not demonstrate that an eruption is imminent. Active calderas around the world commonly experience periods of earthquake swarms and ground deformation without progressing toward an eruption. Before scientists would consider a significant escalation in volcanic hazard, they would expect to observe consistent changes across multiple monitoring systems rather than relying on seismic activity alone. That evidence-based approach remains central to volcanic hazard assessment and helps distinguish between routine episodes of unrest and more substantial changes occurring within the volcanic system. For civil protection authorities, however, even unrest that falls short of an eruption presents significant challenges. Repeated shallow earthquakes can gradually weaken vulnerable buildings, disrupt transportation, damage infrastructure, and create persistent anxiety among residents living above the caldera. Emergency planning, therefore, extends well beyond preparing for a possible eruption. Engineers continue inspecting structures affected by repeated shaking, while emergency managers regularly review evacuation plans, communication systems, and public preparedness measures designed to reduce risk should conditions change. Maintaining readiness during prolonged periods of volcanic unrest is often as important as responding to a single large event. Campi Flegrei remains one of the world's most extensively monitored volcanoes, precisely because so many people live within its boundaries. The lessons learned here extend beyond southern Italy. Similar monitoring strategies are applied at volcanic systems across Iceland, Japan, New Zealand, the United States, and other regions where scientists face the same challenge of distinguishing ordinary volcanic unrest from potentially more significant changes. Every new sequence contributes valuable information that improves forecasting models, strengthens hazard assessments, and enhances understanding of how large calderas evolve over time. The strongest Campi Flegrei earthquake in approximately 40 years will therefore be remembered for more than the damage it caused or the fear it generated. It has provided researchers with one of the most valuable modern datasets collected during an episode of significant unrest within the caldera. By examining thousands of seismic recordings alongside ground deformation, gas emissions, and hydrothermal observations, scientists are gaining a clearer picture of how this remarkable volcanic system adjusts to changing underground pressures. Those insights will not only improve understanding of Campi Flegrei itself, but also contribute to broader research into the behavior of active calderas around the world. For now, the evidence points to a volcanic system that remains active, carefully watched, and scientifically better understood than at any other time in its history. The coming days and weeks will be guided not by speculation, but by continuous observation and rigorous analysis as researchers evaluate every new measurement collected from beneath the Bay of Pozzuoli and the surrounding communities. Whether the current earthquake swarm gradually fades or continues to evolve, one reality remains unchanged. Beneath the cities west of Naples, one of Earth's most complex volcanic systems is still reshaping the crust through slow, persistent geological processes, reminding both scientists and the public that understanding an active caldera is not defined by a single earthquake, but by the long-term patterns that emerge through careful and continuous observation.